Just like we can find the partial sum of an arithmetic sequence, we can find the partial sum of a geometric sequence using the following formula. If we have some geometric sequence, and remember, it has to be a geometric sequence with a common ratio, and we're going to assume that that common ratio is neither 0 or 1, then that partial sum of the sequence is calculated by the first term times 1 minus r to the n over 1 minus r. Let's look at an example where we would use this. We have an individual that has the option of two different jobs, one with employer A, who is offering a yearly increase of $1,250, or employer B, who's offering an increase of 3%, and that the starting salary is both. In what year is the accumulated salary paid by B overtake the accumulated salary paid by A? But what we need to do here is we need to compare the partial sums of the salaries paid by the two employers up through a certain year to answer the question. Notice that in sequence A, employer A, we have an initial salary plus a certain amount every year. So this is going to be defined by n minus 1 times $1,250. It's arithmetic. This sequence of yearly salaries paid by employer B is geometric, and it can be defined by 40,000 times that 1.03 is our R value, because it's going to go by 3% each year, raised to the n minus 1 exponent. Well, we know the partial sum formula for an arithmetic sequence, S sub n, is going to be n times a minus 1 plus that common difference times n minus 1 times n over 2. And the common difference is d for the sequence. And in order to find the partial sums for the first salary, let's instead call this a sub n, so we won't get confused. And so to calculate this, we're going to have a sub n is going to equal 40,000 times n plus the common difference of 1,250 times n minus 1 times n over 2, which we can simplify to 40,000 n plus 625 n squared minus n, or we can simplify it even further to 625 n squared plus 39,375 n for the first employer, given that it's an arithmetic sequence. Using the formula for geometric sequences, we can now calculate B sub n, which is going to be 40,000 times 1 minus 1.03 to the n power over 1 minus 1.03. We can reduce this to 40,000 over 0.03 times 1.03 to the n minus 1. And notice we can do that because this bottom term is going to come negative, and this top term, we're just multiplying through that -1, so we can reverse the order. We can now compare these formulas into accumulated salaries from n up through a certain n value. So in the first year, the cumulative salary would be 40,000. In the second year, you can see that employer A is a bigger accumulative salary, and so on. A stays bigger, A stays bigger, until we reach this year right here, where B surpasses A. As a second example of the partial sums of geometric sequences, let's look at this partial sum from I equals 2 to 7 of 5 times -1/2 raised to the I power. This is a partial sum of a geometric sequence, but as it's written, that first term and the common ratio are not apparent. So a good way to begin is let's write it out. Our first term, remember, we're starting with I is 2, is going to be 5 times -1/2 squared plus 5 times -1/2 cubed, and so on, all the way out to 5 times -1/2 raised to the 7th power. When we multiply those out, this is going to become 5 to the 4th minus 5 to the 8th, all the way up to -5 over 128. From here, we can see that the first term is going to be 5 to the 4th, or 5 over 4. And the common ratio each time we're multiplying by -1/2. Since there are 6 terms in the sum, because remember we started at I equals 2, then we can use the formula that we've been given, and we can say that the partial sum S sub 6 is going to equal A sub 1 times 1 minus R to the 6th over 1 minus R, which gives us 5/4 times 1 minus a -1/2 raised to the 6th, all over 1 minus a -1/2. Simplifying that, we get 5/4 times 1 minus 1 over 64 divided by 3/2, which becomes 5/4 times 63 over 64 times 2/3. Again, when we divide by a fraction, we multiply the reciprocal, or 105 over 128.